In section 5.4, we're going to talk about the sampling distribution and this theorem called the central limit theorem. Essentially, the central limit theorem says that the sampling distribution for sample sizes large enough will take any sort of distribution and turn it into a normal distribution. And so everything that we've learned in 5.1 through 5.3 can be applied to pretty much any distribution after we run it through the central limit theorem. But to begin with, a sampling distribution is the probability distribution of a sample statistic that is found when samples of size n are repeatedly taken from a population. Right, so we're going to take our data set and we're going to just take a bunch of different samples of a certain size n, and then we're going to form a distribution from that. So if the sample statistic is the sample mean, right, we could have used the sample variance or the sample standard deviation, whatever you want to call it. If the sample statistic is the sample mean, then the distribution is called the sampling distribution of sample means. And every sample statistic has a sample distribution. We primarily care about the sampling distribution of sample means. So it has these two properties. The mean of the sample mean, right, and we're going to use mu sub x bar to represent the mean of the sample mean, is equal to the population mean mu. Right, so mu sub x bar is equal to mu, and the standard deviation of the sample mean, this sigma sub x bar, is equal to the population standard deviation sigma divided by the square root of the sample size n. Right, so it's this formula here. Sigma sub x bar is equal to sigma divided by the square root of n. And the standard deviation of the sampling distribution of the sample means is called the standard error of the mean. So I may call it that, you may see it in the textbook as that. Just be aware that the standard error of the mean is just the standard deviation of the sampling distribution of the sample means. Okay, so you write the population values 1, 3, 5, 7 on slips of paper and put them in a box. Then you randomly choose 2 slips of paper with replacement. What we're going to do is first list out all possible samples of size n equals 2, and then we want to calculate the mean of each of those 2 numbers that we pulled. So for instance, right here, each piece of paper that contains a 1, 3, 5, or 7 has the same probability of being selected out of the box. Right, so this is the histogram of the population for X. Right. Now down here, these are all the possible combinations of ways of picking out 2 pieces of paper with replacement, right? So you could pick a 1 and a 1, or you could pick a 1 and a 3, or you could pick a 3 and a 7, or so on and so forth. And for each pair of numbers, you take the sample mean. So that's going to give you numbers 1 through 7 of varying frequency. Right. So these means form the sampling distribution of the sample mean of size 2. Right. So we just created a sampling distribution right here. This is the sampling, the data points that we're looking at, 1 through 7. And so over here, we can find the frequency distribution or the probability distribution for these numbers 1 through 7. So if you see here, 1 pops up only once out of the total of 16 possible numbers that we have over in these 2 columns here, right? So 1 out of 16 is the probability that the average or the mean of pulling 2 numbers is 1. 2 will pop up once, twice, and that's it. So 2 out of 16 is the probability that you'll pick a 2, or that the average of the 2 numbers is a 2. Then if you look at 3, it happens once, twice, 3 times. So 3 out of 16. And you keep doing this so that you end up getting this frequency distribution over here. And lo and behold, that the probability histogram of sampling distributions of X bar is fairly normal, right? So it's symmetric around 4. If you were to take 1 plus 3 plus 5 plus 7, added those up, and then divided it by 4, because you have 4 numbers, 1, 3, 5, 7, you'll get the number 4 as the mean. So the mean of this sampling distribution of X bar is equal to the mean of the actual population itself. Right? And that was the first thing right here, is that the mean of the sampling distribution is the actual honest to goodness mean. And we can do that very explicitly if we want to calculate it as well. So mu sub X bar, remember that since this is a probability distribution, the definition of the mean is the sum of X times the probability of X. Right, and so over here, the first value is 1 times the probability, which is 1/16, plus the next value is 2 with a probability of 2/16, plus the next value is 3 with a probability of 3/16, then 4 with a probability of 4/16. Then we have the number 5 with a probability of 3/16, and this just keeps going. So 6 and 2/16 plus 7 and 1/16. If you were to add this all up, you'd end up getting 4. All right, so this is symmetric around its mean. And we could calculate the variance. I suggest you pause the video and calculate the variance of this distribution here. All right, and just to recall that, it's going to be the sum of each value minus the mean that we found, squared times the probability of that value. All right, take a second and actually calculate that out. Pause the video and maybe do that. Before we simplify the fraction, you should get 40/16, which is going to simplify to 5/2. And notice that 5 was the variance of the original population. So this was sigma squared of the original population, and 2 was the number that we took as sample sizes. And then if we want to find the standard deviation, remember that the standard deviation is the square root of the variance, which we know that the variance is 5/2. And if you remember back to your rules of exponents, this becomes square root 5 over square root 2. Right? You can break up square roots over division. And square root 5 is the standard deviation of the population. And 2 was, again, the sample size that we took. So this is really the population standard deviation divided by the square root of the sample size, which matches up with the properties of the sampling distribution of sample means.